Hello? All right, cool. So the next session we have is DDC, Distributed Disaggregated Chassis. There's a lot of history behind it. Anybody that has built networks knows, how, everything was control plane, data plane, one platform. Then we went into, distributing the fib, into line cards, creating multi-chassis routers, and now we are here at this stage of taking the leaf spine architectures to distributed, disaggregated. With that, we've got a great set of presenters here, Rehan, Philippe, and Kay, gonna walk us through. Thank you.
All right. Hello, everyone. Thank you for coming to our session. Really appreciate you coming in. Like Ripin said, we'll be talking about the latest version of DDC3. And then I wanted to highlight some of our partners that we've been working with to come up with the specifications. We've been doing this for the past few years. So I have Kai from UFI-Space, Felipe from Intel, and then a few of our other partners that are part of it have been from DriveNets and HPE that are also participating in some of the contributions that we're discussing with you today. So as Ripin said, we started on this journey a few years back. So we've been doing version 1, version 2, version 3. And then in this version, what we want to highlight is what we have is we're going to be expanding the current DDC architecture with the next generation of hardware. And then today, what we have in the network, especially in the AT&T network that we've deployed, we've been doing 100, 400 gig. And what we're specifying in the next generation of contribution is our 800 gig chassis, and that sort of highlights the extension of capacity that we would be able to take out of that or take that system to, right? So today, the system that we have with 100, 400 gig is based on our J2 and Ramon 1 and Jericho 2 hardware, which extends up to 192 terabits capacity of routers. And this next generation would allow us to expand that capacity and increase it up to 900 plus terabits per box, right? And it also sort of gives us the opportunity to interoperate existing clusters. So we're not going to be doing a replacement, but we would be expanding the current architecture. So it allows us to grow as you need, right? So as the need for 800 gig comes across or comes up, you can extend your network, add new capabilities into that, and extend the system to give you the 800 gig capacity connections that you need. And then also, we'll talk in the hardware, it gives you the PTP timing support within the system now. There are some NOS enhancements that are coming part of this. There is also some Intel enhancement that we're adding into the system as well. And then one point I would highlight is right now we're not discussing the migration steps as such, right? So we're just specifying the hardware platform infrastructure, what would it look like, what does it contain, what enhancements are there, but we could have separate discussions about how do you migrate existing cluster chassis systems or DDCs to the next generation, how do you do that migration. A few key points in the specifications here is we started in 2022 with version 1. With version 2, we added some new capacity for 400 gig, and then we also added an option for potential component which is in there that we'll talk about is NCC and CM combined. And then in the latest specifications, we're adding 800 gig introduction. We're adding the new NCPs that are based on Jericho 3, which would be capable of doing 800 gig, as well as timing support. And then also from Intel side, we'll be adding the new Ice Lake CPU into the system. And then also for management, we're proposing to start going more towards Redfish on the NCC, which is the controller part of the DDC architecture. This slide points out the way we wanted to look at this is in terms of utilizing how do you, because the flexibility of the system is such that you can have as many combinations, permutation, iterations that you would like. But the way we wanted to do this is to simplify for our operational folks. We came up with 4 main ideas of architecture to say, look, if you have a capacity need of about 14.4T, you can start with a single slot system. And then we came up with the idea of a small cluster and a medium cluster and a large cluster. So depending on your need, you can choose one of these, or you can have your own design that you want to come up with for your network. You can have somewhere in between, but this is something that we have decided or selected as an option for our operational team. So if they want to deploy a smaller system, they can start with a small cluster, and then as we migrate their larger sites, we can go deploy a medium cluster, and for our largest SNRCs where we have a huge demand of capacity and interface connections, we can go deploy a large cluster. So that's how we deploy these, and then this sort of shows you how much capacity each of these clusters would have in terms of terabytes, and how many rack space, et cetera. The NCP5 units, which we call it, the J3 units, are needed for such connections, right? And then NCFs would be your fabric connection, so you will have the fabric in between, and then you have the line card or the network connection platform, the NCP on the edges. This slide is from our friends in DriveNets. This points out some of the key elements that they're adding into the system, and as I was saying, it gives you a higher scale with capability to do J3R3 800 gig, and it also, as a software, one of our requirements was that you need to be able to mix and match. So you can upgrade the fabric, go to an 800 gig capable fabric, but you don't have to put the NCP5, which is the 800 gig card, right away in the day one. You can use your existing line cards that you have, existing router networks, continue using it, and as your need comes up, you can go in and apply new NCP5 into that cluster, so it would be able to operate in a hybrid mode. And then also, as part of migration, you don't have to migrate the full cluster at a time. You can pick and choose. You can decide which fabric. As you add more NCP and NCFs into your networks, you can start upgrading your capacity and capability in the network. There are some other additional use cases that they're coming up in this that will give you additional AI workload enhancements, et cetera. So they have installed, you can discuss with them, sir. Next slide, I'll hand over to Felipe to discuss some of the Intel technology that we're introducing into this.
Thank you, Rehan. So for this spec, Intel contributed a number of initiatives. We brought the CPU. We were talking before about the clock synchronization. For this particular slide, what we wanted to double check or bring the magnifying glass is around our virtual RAID on CPU technology. This was a very relevant contribution because what it brings is increases the level of reliability on your white box. We saw in previous instances, on previous specs, that the box reliability was very dependent on the single drive that was on the box. So there was a need for increasing the box reliability. We investigated with our partners here different options around having just additional drives or having a hardware drive, hardware RAID controller, or having a software-based implementation. And we contributed to VROC. Basically what it means is you have the entire functionality of an external RAID controller that sits on PCI Express. You run that capability as part of your BIOS. So BIOS is going to be able to discover and enumerate hard drives that exist within the SATA or a PCI Express domain, and it's going to generate a RAID 0, RAID 1, or RAID 5 volume that will be exposed to the OS. That means that the OS, while maybe aware of it, regardless of which drive may fail, is still the system is going to be able to boot. So you're going to have a significant increase on reliability for your box. We provided, for your benefit, we provided a kind of a thorough table here. I'm not going to go through the entire thing. Basically, the bottom line of this technology is that when you look at the RAID hardware as a added device on the platform versus our VROC capability, we provide all the functionality, and we also exceed what Linux RAID can deliver, right? Everybody's very worried right now about power consumption and efficiency. What we have demonstrated through various different benchmarks is that we provide better IOPS, we provide lower latency, and we provide better efficiency because we are removing one element in the stack. So with that, thank you very much, and we will pass it on to Kay. Thank you.
One more slide. Thank you, Felipe. So this is the next piece in the puzzle here. which is the controller part of the architecture. Today, we were using Gen 10 systems from HP. We're part of this new specifications. We're expanding that also to include the next generation of HP hardware, which can run the controller software in it. And then eventually, we wanted to think about how do we look at the NCC NCM in the future as well. So if you're familiar with the architecture, the NCC is the controller brain of the system that runs all the management software on it. Kai?
One more.
So yeah, this slide is sort of covering the differences between Gen 10 and Gen 11 servers. So the main difference is going from Cascade Lake server CPU to a Sapphire Red with more capabilities in HBM.
Thank you. So just kind of recap before we dive into the hardware design. The whole idea of DDC, disaggregated chassis design, distributed disaggregated chassis design, just kind of 30-second recap, is functionally we break down a traditional chassis by function into this pizza box. So we can talk about, the HP PoLion, that is actually your route processor, basically like running all the main routing function. And then we, in the next 10 minutes, we're going to talk about functionally the pizza box we built for the switching fabric and also the line card. So that's really like what this is all about. Now, why are we doing this? Okay, it's really one and only one main reason is to allow the solution to scale horizontally. So that's really the whole selling point of trying to do this distributed architecture. All right, so Rehan and Felipe talk about some of the other function on the DDC cluster. Like the route processor. I'm going to be talking about in the next 10 minutes the switching fabric as well as the line card. So starting with the line card, okay? Not too long ago, maybe about a quarter ago, Broadcom announced officially their latest Jericho family, which is called the Jericho 3. And the box that we bring to the table today is actually based on the J3 design. And working with the J3, there is another component, another chipset called the Ramon 3, which is doing the switching fabric, okay? So together, it's kind of like a clock topology with the switching fabric and the line card to make up this cluster horizontally. And the whole thing looks like one virtual switch from an operation perspective. All right, so that's kind of the background. What you're seeing on this picture is the Jericho 3 design that we are building, where we are almost done. And we call it the NCP Network Cloud Platform, and we are at number 5 now, all right? So that implies they are number, previous number, which I'll share with you in a second. What is the selling point or the use case? I mean, it's kind of fun and excited to talk about Jericho 3, but what is really for you? Really for you is the following use case. Now we can bring in a high-density 400 gig connection into a pizza box with a very clear path migration into 800 gig, including all the coherence optic, the CL, CL+, with super long distance. So when we build a box, we have to remember what is the use case for our end user customer. Why do you care about this box? It's not because they have a J3 label. It's because of all these high density 400, 800 gig coherence optic with the super long distance. This box, just like any boxes that we build, come with a lot of telco feature. And we're going to talk a little bit in the next slide. But one thing I really want to highlight is the PTP timing support. Is known as the IEEE 1588 version 2. The PTP precision timing protocol support is very important when we design a telco carrier because it's basically allowing us to send PTP packet from a timing perspective, cascade a higher number of devices from one point to another, so that we'll be able to preserve the timing and all that. And there are a few other features that we will address as well. So to summarize, this is a box that is focusing on high density 400 gig and 800 gig migration with fully fabric support. And oh, by the way, I should mention, we color code this port. The blue one that you see, those are network interface. They talk Ethernet, they talk jumbo frame. The one on the red color, those are cell switching. They are specifically from the Jericho 3 talking to the Ramon. They do cell switching, not Ethernet packet. All right? So here's a block diagram we like to share with the audience. We color code them. You see 4 different colors here. Right in the center, that is the blue one. That is the Jericho 3 chipset. It's a 5 nanometer chipset switching at 14.4 terabit per second. I want to kind of put this in perspective. When you look at the Jericho 2 is at 4.8. So from Jericho 2 to Jericho 3, that's another chip in between called the Jericho 2 Plus, the 2C Plus. That one is switching at 7.2. So I kind of want to bring you back to the history from 4.8 with the J2 generation into the 7.2, something in the middle. When we now at Jericho 3, we are switching at 14.4 terabit per second. That's how we can build a non-blocking architecture with such a high density 400 gig support migration to the 800 gig when the market needs them, all right? So right in the center where the blue is, that is the data plane. If I can call your attention to the left upper corner, that is the control plane with the orange color. That is the Intel processor where you will be running your network operating system of your choice. It's a disaggregator model, so it's kind of like a option. You can pick and choose the type of network operating system vendor you want to run. On my right-hand side, that is the green block. That is the timing. That is all the PTP circuitry. And we utilize a solution called from Microchip Microsemi with some of our own FPGA design into that green block. The reason we take natively the Microchip Microsemi PTP timing, but we had to include some of our FPGA programming is we had to fit some of the signal back into something called the Broadcom format, back into the data plane. So Jericho 3 understands some of the signaling. All the translation are done with the FPGA that we develop in-house. I mentioned there are 4 processors. We talk about the control plane, which is the Intel, the data plane, the Jericho 3, the timing. The last one is the tiny box underneath the Intel box is our BMC. Basically, it's another separate processor we use to do all the housekeeping. We want the Intel processor to do what it's supposed to do, which is to run the network operating system, manage all the routing switching function to push to the data plane. All the housekeeping, we have a separate processor to do that. So that's kind of the design. And underneath, on the bottom, you see all the I/O port with the 400 gig that we support, and then with the migration to the 800 gig. Now, we just talked about the line card. Let's talk about the switching fabric. The switching fabric is based on the next generation of the Ramon chipset that Broadcom called them Ramon 3. This is a single Ramon 3 design that supports up to 64 port of cell switching at 800 gig. Now, on the previously, I talked about the 400 gig with the migration to 800. Remember, the line card is connecting to your other devices, maybe your remote node, maybe a server farm or whatnot. This device only talking to the cell switching connection into the Jericho 3 and nothing else. So that's why from the get-go, I can make this 800 gig because I know it will only talk to the Jericho 3. So that's why this thing has no need to have the 400, we can just do the 800. Now, of course, for backward compatibility, we can do the 400 with some of the older boxes like the J2 cell switching and all that. So this is a single Ramon 3 design. Now, the block diagram, similarly, right in the center is the Ramon chipset that is driving all the cell switching port. And then we have the Intel processor on your left upper corner. We, just for the efficiency of our supply chain, we use exactly the same type of Intel processor as the line card, just to make the support a little bit easier. And then we also have the housekeeping chipset that I talk about on the line card as well. So this is the fabric. So to summarize, the fabric and the line card provide this clock connection, kind of like a spine and leaf, and it's designed to scale horizontally. Along with the network controller we can talk about with the HP PoLion, this whole thing make up a virtual switch to scale horizontally. As your network grow, you keep adding more line card. When you run out of that, you keep adding a little bit more switching fabric to make up this node. The NCC we can talk about, that stay as a cluster. That doesn't need to scale. It's really the switching fabric and the line card to make up this one virtual switch. Now, we talk about DDC V3 today. And when we talk about V3, that means there's a V2 and a V1, all right? So this table, basically, if you want to download a copy of the slide, talks about how the evolving of the original V1, V2, and now we're into V3 with the NCP5. And then similarly, on the switching fabric, we are giving you the same comparison table, how the previous generation of the Ramon into this one right here. And this is one of the last thing I want to talk about is the importance of the optic we support. So we highlight the J3 and the R3 on the top, and we kind of color code them, all the different type of optic we had tested in our lab in Taiwan headquarters. So that gives you a reference table, depends on the distance and the speed that you need, and more importantly, the power dissipation, the heat dissipation that you need for that kind of, so we have a full list of optic family. All right. Last thing I want to talk about is compliant. Anything going into the central office has to be NAPS compliant. In the case of AT&T, we have additional compliance with the TP76200 that we have to be all compliance with the temperature and all these other things. So this box or any boxes we build for carrier has to be compliant with the NAPS 3 and all that. Last thing in the last 30 seconds, call to action. We have everything we talk about, that I talk about, Rehan talk about, and Intel talk about is in the Experience Center today. Please come by, please take a look at the J3, all the cabling and the whole rack. We're right in the middle of the Experience Center. Anybody welcome to come by and take a look at it. The documentation has been updated at the OCP library with the link here. So with that, I'll turn this back to our host.
Oh, great. Great presentation. Thank you.
Thank you.
I think we've got time for one question. If the next presenter wants to come and set up, we can do that, but we have time for one question.
Thank you. Great presentation.
Thank you.
Could you speak, so spec is one thing. Could you speak to what is the maximal port that you have deployed in production at any deployment with either a J2C plus or, I mean, J3 is pretty new, but what is the maximum scale you have actually deployed?
So I'll take that. So in our network, and since we started a few years back, right? So like I showed earlier, we have different combinations. So we have nationwide, we deploy these clusters in different combinations. So the largest cities that we have deployed in the large cluster topology, and that takes you up to 48 NCP1 line cards, which is capable of, I'm not sure the math is giving you, 48 times 100 ports in the system, right? So then again, what we are looking at, because the reason why we're looking at this is some of those large SNRCs are running out of port capacity. Not the traffic congestion, et cetera, but the port itself, the connection capacity. So that's why we started looking at J3, R3, which is now going to expand to 64 of those line cards with the Ramon 3 fabric. So that will give us a lot more 400 as well as 100 and 800 gig ports.
All right, thank you. They're going to be here. This is a very important topic, so please grab them.